Wisconsin H alpha map emission, all these density fluctuations, and they nicely fit the Kolmogorov law. So how would this change the problem of reconnection? And let me show my version of reconnection. And this is a change of the topology of the fluxes. So we have two fluxes, and the problem of reconnection is to answer the question, what will happen if we have two fluxes which try to pass through each other? Whether we'll have this knot, there's a no reconnection, or there will be a change of the geometry. And this is a very generic problem. Well, this is a Sweet-Parker model, and you can see easily why a connection in the classical Sweet-Parker model is very slow. Because you have plasma coming at the scale of astrophysical dimension, Lx. And here, a connection, the process of dissipation of magnetic field, is taking place over microphysically thin layer. And the plasma is being ejected at alpha velocity. So you write the equation for the conservation of mass. And you get the alpha velocity, and then this is a tiny factor, microphysical quantity over astrophysical quantity. So this explains why a connection is slow in the classical scheme. What is missing in this scheme? And I claim that turbulence. If you allow turbulence to exist in the system, which we know that it exists, in this case, the outflow is not anymore limited by microphysical parameter. It is, can be, this delta can be comparable with Lx if turbulence is sufficiently strong. At the same time, it all answers the question why a connection is both slow and fast. Because we know for flares we need periods of slow a connection to accumulate the flux. In this case, indeed, if turbulence is weak, in this case we have delta small. This magnetic field wandering is small, and therefore a connection speed is small. Right, is this unprecedented? It's not unprecedented. What's your suggestion? How much time would you need to wait before your sugar is diffuses in a cup of coffee? And you know the diffusion constant, and you do the calculation, and you need to wait for months. It's too long. You introduce turbulence, and turbulence does the job. So this was our model suggested in '99. Recently, we addressed this problem with Greg Eink and related our model to the well-known concept of the Richardson diffusion. Richardson, before Kolmogorov, studied the spread of the volcanic ashes. And he came to the law, which is termed Richardson law of superdiffusion, where unlike usual diffusion, the squared displacement changes not with time, but the time cubed. This is a law which also works in MHD. And these are recent proofs of Richardson diffusion, and this is diffusion in space. And this is a recent Nature paper, Eink et al., where this was also shown to be present in time. So many shots, time shots, frames were studied, and Richardson diffusion was proven. From Richardson diffusion, we get also scaling that we suggested some time ago. But there is a direct way to test the scaling. We can just drive turbulence and see what's happening with the reconnection rate. And this is the prediction for the turbulent A connection. And different points correspond to different guide field and actually different ways of driving turbulence, both in real space and in the Fourier space. This is quite, I think, adequate correspondence. So, whether or not microphysics plays a role in a connection is an open question, I think. It depends on the scale of your system, scale of your current sheet. If you are, for example, thickness of your current sheet is comparable to the Larmor radius, surely it does. But in astrophysical systems, I believe microphysics in turbulent system does not matter. These are simulations which show different levels of anomalous resistivity, which should correspond to the microphysical processes of enhanced reconnection, and it does not depend on reconnection rate, does not depend on these parameters. So, well, these are MHD simulations. What do we have in 3D peak simulations? In 3D peak simulations, we observe formation of turbulent structures. These are actually Kramer-Badi et al. Simulations, and they show development of Kelvin-Helmholtz instability. And as soon as you introduce turbulence, physics change. The instabilities, for example, tearing instability is being suppressed by ambient turbulence. These are simulations by Berezniak. These are MHD simulations, but you see the same structures. Berezniak used MHD simulations with closed boundary conditions, so periodic boundary conditions, and therefore he could not study the system for a long time. We managed to do this with boundary conditions which were open boundary conditions, and here's the plane going through our box, and you see formation of turbulence. We measure spectrum of this turbulence, and this corresponds to the Goldrich-Seidra scaling. So we have real turbulence formed when we don't have initial turbulence. Turbulence is produced by a connection. So I claim that turbulent A connection is a generic astrophysical A connection process. These are the same simulations with magnetic fields and currents shown. So about solar flares, Jim mentioned solar flares as the test bed. I believe that turbulent A connection explains solar flares because we can have periods of accumulation of flux, and then A connection induces the outflow, and this outflow makes the system turbulent, and this enhances A connection rate and resulting in explosions. So there were also measurements of current sheets. There were also measurements of our prediction that triggering of reconnection, that we can have places where we have reconnection, it sends alpha waves and induces a connection in the adjacent region. These are CH et al. Measurements. And moreover, a connection was found both fast collisional and collisionless plasma. So it shouldn't really depend on what is happening on the microphysical level. So this is a spectacular event of the solar flare. Right, so I think there is a big convergence of ideas on a connection. In 1999, the whole A connection, Petchik time X point A connection was the dominant idea, and it was considered that the Hall effect is absolutely required. We were claiming Hall effect is not required, and fully 3D turbulent reconnection can happen both in collisional and collisionless media. We have now tearing reconnection, and Hall effect, many researchers claim, is not required. Moreover, this new simulations in 3D peak also show a development of a connection which I believe is induced by turbulence. So let's go to the second point, which is the acceleration of particles. In the model of turbulent reconnection, the contraction of reconnecting magnetic field lines like that is natural, and it's happening all over the volume. This is a volume type effect, so we have the whole volume of such three-dimensional loops. And this is a reproduction from some old paper. And this is the spectrum, which is different from what Jim showed us that we obtained a few years ago. Jim takes into account back reaction. We did not. So therefore, probably this can be explained that we have. Now there are many applications of the mechanism to different systems. The system of these islands can be reproduced and studied in 2D, for example, also in MHD limit, and we easily see a picture which is similar to what Jim just showed us. So I will not develop on us. But I would like to stress that not only a parallel component can be accelerated. It can be accelerated in 3D also perpendicular component. Consider a particle rotating around the guide field, and this is a very efficient first order acceleration when we have a convergent flow. And these convergent flows are happening all over the volume. So we can have acceleration, and these are three-dimensional results of studies of acceleration, where we have both parallel and perpendicular component accelerated, and here we have Sweet-Park acceleration, here we have turbulent acceleration, which is a second-order Fermi acceleration, and we have this acceleration in our turbulent data cubes. So I will not dwell upon this. Actually, these are measurements of anomalous cosmic rays. It can be one of the applications. Another application, probably more relevant to this conference, is application to the gamma ray bursts. And there was a recent model, Zhang and Yan, which used our model to explain some features of the gamma ray bursts. So let me go, and I'm running out of time dramatically. So to the last point of my talk, I will be very brief. I think we should not forget about shock acceleration. Shock acceleration is a very well-known process. You have also this mirrors coming together, and the particles bouncing back and forth between the mirrors are getting accelerated. So now I discussed Richardson diffusion in terms of reconnection. Richardson diffusion is also important in terms of acceleration. Why? Because it predicts a fast divergence of magnetic field lines. And how can it be important? This is the ratio of the diffusion coefficients perpendicular and parallel in the classical study of Randy Jokopi, and it's related to the mean free path and Larmor radius of your particles. On the basis of this expression, it is claimed that perpendicular acceleration is much more efficient than parallel acceleration. However, this assumes, and Randy is completely explicit about that, that there is no field wandering. In the presence of this fast superdiffusion, the situation is very dramatically different, in fact. And I don't have time to discuss the differences, but in fact, this is approximation is not working, and the perpendicular acceleration is not more efficient. Moreover, what we need to deal with in shock acceleration, we also need to deal with the with the generation of magnetic fields in the precursor. And this is some model where a precursor interacts with pre-existing density and homogeneities in the interstellar media and generates magnetic field. This can bring us to the energies of 10 to the 15 eV that was discussed in the beginning of this conference. This is what's happening in turbulent dynamo, and what I would like to just say that this process, at least our estimates show, can be more efficient than very popular right now current instability, Bell's instability, which generates magnetic field in front of the shocks. So I would conclude that it's not good to dismiss the physics of shocks while talking about the research in the next 10 years. So this is my last slide. And what I was trying to explain to you is that turbulence and reconnection are two sides of the same coin. Turbulence, in fact, to be self-consistent. Goldberg-Seidler model, which is the most accepted model of turbulence, does require fast reconnection at the rates that I discussed. Turbulence requires a connection. A connection in astrophysical systems does require turbulence. And if you don't have turbulence, a connection would create turbulence. In terms of the particle acceleration, it's one of the applications of a connection, and it can induce the acceleration in terms of both of parallel momentum, the slingshot mechanism that Jim mentioned, and also in terms of the perpendicular momentum. So, thank you.
This question really arises from your words were lost in the echoes in the room. You said that perpendicular acceleration in shocks with the turbulence is or is not fast.
Again?
For a perpendicular shock, acceleration is or isn't the...
Perpendicular shock acceleration does not solve the problems that people believe that it solves. Usually it is considered to be very efficient, at least by some people.
By some people?
Yes, by some people, but it's not, the physics has changed as soon as you take into account Richardson diffusion.
Yeah, actually, I wanted to ask, with the turbulence also amplifies field. And so the dynamo action that you have on small scales, so how do you see that fit in with your picture here?
Yeah, this is what I did not really have time to describe this. This is a turbulence spectrum which is created by the precursor interacting with density and homogeneities. And as a result of interaction with magnetic field, you have an increase of the magnetic field energy, and this creates the higher magnetic field in front of the shock. But by the way, it's also because we create this magnetic field structure, I would claim that this can allow us a different way of accelerating particles in shocks, which does not require collisions. So in some sense, Jim was saying that it's a very weird way of acceleration in a connection sites, which does not require collisions, and it's happening with anisotropic distribution. What is happening when we have this structure is the same. We have also acceleration with anisotropic distribution of particles.